Hello everyone, welcome to this channel and welcome to this video. I am Saptarshi Mukherjee. I am a software engineer 3 at Google and I'm a competitive programmer. So in this video, I'll be discussing a very interesting topic, DP plus prefix tricks. I actually found that there are not too many tutorials on this on YouTube, but I found this as a very effective technique to grow in competitive programming. You have many problems out there in recent lead code problems, lead code contests, and Codeforces contests. And I'm sure that by learning this technique, you'll be actually able to perform better in those contests. So this session is going to discuss this particular technique for these three problems that I picked. The first is a classical problem. You might have faced this: buy and sell stocks. 4. You have a hard problem of lead code contest, weekly contest 388 that I picked. That is the last problem of that contest. And you finally have this problem, CF round 932, problem C. So yeah, before this I have some other videos on DP. If you want, you can take a quick look at some of them. So you will find select and not select DP. You will find this particular problem I've discussed over there, blocking elements. This was a Codeforces D problem. And then I took another session on DP on trees. There I discussed the same thing on a one-dimensional way in an array, and then I took it to the two-dimensional way. So these are two DP things that you can actually look up from my previous videos. And in this video, we are going to focus on DP plus prefix trees. So yeah, this is not a very syllabus kind of a topic. There is no particular chapter you will find in competitive programming sites, etc. anywhere. But this is a very effective thing. So you will find some problems, you will find a good lot of problems where you will see you are given n elements and you have to do k selections. So the selections can be selections of elements or selections of pairs of elements or selections of subarrays either. But one thing is that the selections will be sequential. You cannot have overlapping selections, something like that. So disjoint selections. So you have n elements and you have to do k selections, and then what is the best that you get after k selections? That is what those questions are usually based on. So what we find is that, okay, if you are solving it for, let's say, k selections, if you know the best answers for k minus 1 selections, let's say you are solving for k selections, and let's say you know the answer for k minus 1 selections, then that helps you in finding the answer for this. Now, based on k minus 1 selections, sometimes it happens that based on one element you don't get the answer. Sometimes a lot of elements together help you in the answer. And sometimes not just the DP states themselves. Not just this DP state will provide you this answer. Sometimes some other computation with those DP states. So sometimes you will see that for DPIJ, DPI minus 1, J minus 1, DPI minus 1, J minus 2, DPI minus 1, J minus 3. And with each of them, some other component will also get added. Sometimes not a constant component, but some similar variable component gets added. So somewhere we have to use this prefix some kind of technique or prefix kind of technique, prefix min, prefix max, prefix sum, many other things. That actually helps us in solving the entire problem. So through these three problems that I picked up from three different places, I'll actually discuss them. And you will find these are quite frequent. All of these, the first one is a classical problem, which you have to learn for your interviews and placement preparations and all those things. These two problems came up in the last 1 week in lead code and Codeforces. And there are also other problems I've seen which also have slightly more difficult problems or concepts as well with them. That is why I have not picked up those problems. But at the end of the session, maybe I can tell you that you can solve them as your homeworks by using this kind of technique. So okay, let's see. The first problem, buy and sell stocks 4. So what this problem says is, you are given an integer array, prices. You are given an integer array prices where prices I is the price of a given stock on the ith day and an integer k. Find the maximum profit you can achieve. You may complete at most k transactions. That is, you can buy at most k times and sell at most k times, but this is the sequential part. You must sell the stock before you buy again. So you must sell on the ith day to be able to buy on the I plus 1th day. Right? Okay, so you can sell at most k times. We will take care of this at most at the end. Let us imagine that, okay, if we have to do k times, what is the best we can achieve? Let us see. So first of all, understanding the problem. If this is my prices on 6 different days, um, for convenience, for the time being, I can take this as one indexed, 1, 2, 3, 4, 5, 6. Let's say these are all one indexed. And then what I can say is, okay, if I buy on this day and sell on this day, and if I buy on this day and let's say sell on this day, these are my two transactions. I am following the rule. I am buying after I am selling the previous one. So what is my profit? My profit of B2S is basically 3. 6 minus 3 is 3. 6 minus 3, sell minus buying. And the difference over here, 5 to 3 basically is minus 2. So when I add them, basically I get 1. That is my total profit. If I say, hey, I will do it slightly differently, I will not buy on this day, on the 4th day, I'll rather buy on the 5th day. Then the transaction becomes something like this. B2S, it basically, this one will give me 3, the same as before. This one will give me 3. This is better. 3 plus 3, 6. Now if I say, hey, instead of this one, I will take a different one. I will buy on this day and sell on this day. So this particular thing. What does this give me? 6 minus 2 gives me 4. So 4 plus 3, 4 plus 3, 4 plus 3 gives me 7. So 7 is the maximum profit after two transactions, two non-overlapping transactions. So how can my DP state be based on this? This is a standard notation of the same thing, my DP state, that DP of I to J is basically the maximum profit with I transactions such that the last sale is at or before the jth day. So I'm restricting what is my last day of sale. That is one of my DP state indexes, and the transactions, number of transactions, is another DP state. So how can I solve this problem? I can basically say, hey, for let's say DP of, let's say you want to consider up to the 4th day. If your sale is up to the 4th day, and if you are doing two transactions, what is the maximum profit you can achieve? You can say one possibility is I will not go up to the 4th day. I will go up to the 3rd day only. So one possibility is that you will take only DP 2, 3. You will not go up to the 4th day. That is a simple possibility. What next? Let's say I will say, okay, I buy on the 3rd day and I sell on the 4th day. So I am saying that, okay, you buy, you sell on the 4th day, and you buy on the 3rd day. So over here it will basically be 4 minus 3, that is 5 minus 6 minus 1. So if you buy on this day and sell on this day, this is what you will get. Fine. Prices 4 minus prices 3 plus DP of what was the best before this day. You bought on the 3rd day. What is the best before this 3rd day? That is, with one transaction before the 3rd day, that is up to the 2nd day, what is the best you got? This is the best you got. Similarly, if you say that, okay, I will not buy on the 3rd day, I will buy on the 2nd day. So you're basically saying, hey, I will sell on the 4th day, but I will buy on the 2nd day. That means before the 2nd day, this is the DP state, DP of 1, 1. And if you say, hey, I will buy on the 1st day, you may wish to buy on the 1st day. So you may say, okay, then DP first, the DP of the first transaction up to the 0th day. That is what we want. Somewhat this is how the computation will range from. These are my 4 possibilities, right? So what are the 4 possibilities? I don't sell on the 4th day, then this is the possibility. Now if I sell on the 4th day, then which days I can buy? If I sell on the 4th day, then this part is fixed. Which days can I buy? On the 3rd day, 2nd day, 1st day. Now if I buy on the 2nd day, what is my variable part? The best thing before the 3rd day minus the price of the 3rd day the best thing before the second day minus the price of the second day, the best thing before the first day minus the price of the first day. So what do you see? The relation that you see over here is okay. If I want to buy on the, if I decide to buy on the lth day and sell on the jth day, this basically gives me dp of I minus 1, I minus 1th transaction, L minus, okay, you're buying on the lth day, so I can say that before the lth day, I'm interested in before the lth day. Just a second. Yes, I'm interested in before the lth day. So this is the best up to the L minus 1th day, minus, or you can say plus the price of jth day, price of the jth day, minus the price of the lth day, prices of the lth day. So these two are functions of L, and what I need is basically the maximum. I need the maximum of these four possibilities. So somewhere I can say, okay, among these yellow parts, this part minus this part, this part minus this part, this part minus this part, these are the only different parts. Prices 4 is common, this part was common. So these are the only three different parts, which means that this is my deciding factor. Prices I minus 1, L minus 1, minus prices L. So this is my deciding factor. dp I minus 1, L minus 1, that is the maximum profit before that, minus the price of buying on that lth day. You need to find out the maximum out of all possible L. What are the possible L? L will go from 1 up to j minus 1, j minus 1, when you want to sell on the jth day. So what is the total computation going to be? dp of ij is equal to the maximum of dp of I minus 1, sorry, ij minus 1, that is up with I transactions, what is the best you can do up to the previous day, comma, what is the maximum you can achieve using this. So maximum, and this is a common factor, so prices of j plus the below maximum. So this is one item. So we will take the maximum of these two things, this dp and this total thing. That gives us the answer. So what is this? This is like sell before the jth day. This is sell before jth day. And this one is sell on jth day. And this one will tell you, okay, buy on lth day. That's it. So using this, you can solve the problem. You have basically reduced it. You have said, I'll solve it transaction by transaction. First transaction, one row. Second transaction, second row. Third transaction, third row. And so on. And for each DP state, you don't have to look at so many DP states together. This is the prefix optimization. If you did not do the optimization, you would have to look at all these steps together. So if you basically say, okay, I will just solve this thing, you have to look at from 1 to j minus 1, which means if you do a brute force kind of thing for these DP states, for each DP state, this will be a big O n kind of computation. This can go up to a big O n kind of computation. And this big O n computation, you can reduce it to big O1 using a prefix max. If you do a prefix max, saying that, okay, as I move ahead along this L, or as I move ahead along this J, I will keep on computing this. So as I move ahead with J, I will include that J minus 1 for that particular computation. So for a certain J, so for J minus 1, I have already taken up to J minus 2. For J minus 1, I have already considered up to J minus 2. So for j, I just have to include this term for j minus 1. That's it. That's exactly what I'll be doing. So in this way, using such a prefix, carry forward variable, you can optimize this. You don't have to spend big O n behind each state. So overall, the time complexity will go up to big O1 for every state, which means a total of big O n into k. So it will be a total of big O n into k time complexity, and the space complexity will go up to big O n into k, which can be optimized if you want. For competitive programming problems, usually you don't need to optimize, but you can optimize it to, you can optimize to say, okay, I need only 2 rows at a time. So using that trick, you can optimize the space. But let us see. Let us see how I've implemented it. So this is the profit array. This is the answer that I'll be returning. Now, it is not compulsory to use k transactions. I can use less than k transactions also. That is why I'm taking the maximum at the end. That, okay, for each I, up to I transactions, for I transactions, tell me what is the best answer you get, which is profit in. That is what we'll be returning. So profit is basically containing the DP state. So what am I doing over here? Local max, I have to find out the maximum. So I'm starting that with the minimum possible value. And then I'm saying, okay, as you move to a j, you need to consider this. So remember, there is an adjustment. Over here, I started the prices thing with 1. I did it from 1 to 6. Actually, it is from 0 to 5. So what I have written as L for prices, if I've written prices L, over there I have to write prices L plus 1. If I wrote prices L minus 1, over there I have to write prices L, something like that. So basically I have to add 1 because over there the range is not 1 to 6, the range is 0 to 5. So as you can see over here, I'm doing L minus 1 minus L. Over there you will say, okay, the L over here means something else over there. You will find that adjustment over there. You will find maybe this will become L minus 2 over there. Let us see. Prices j minus 2. So I'll read through the logic. Just a second. DP of minus prices L. Yes. So over there, according to that, it will be prices L minus 1, according to that logic, right? According to that logic, this will be prices L minus 1, because there it is from 0 to n minus 1. So in my 1 to n, this means L, that means over there it means L minus 1. So basically L minus 1 and L minus 1, they will become same. That is why I have the same indexes for both of them. Now let us see. Yeah. Profit of I minus 1, j minus 2 minus prices j minus 2. I'm doing the exact thing, and these are some sanity checks I'm doing so that I don't face a difficult situation. Prices j minus 2. You can try without this kind of sanity checks as well. You can see what you get. Depends on how you have initialized, etc. So yeah. Finally, this is the kind of relation. Profit of I j minus 1, the left state, and then current price where you're selling, plus whatever is the local max, the maximum before this, that is this particular thing. So I am basically remembering that in local max. One meaningful interpretation of this is that, okay, yes, this is needed because I'm doing j minus 2. So basically when it is j equal to 1, I can't buy anything before that date. For j equal to 1, this basically means my first date. I can't buy anything before my first day. So when it is j equal to, that time only I am considering, okay, I have sold something. So then it is logical. Then I'm basically doing the maximization over here, and I'm adding that local maximum over here. Finally, answer equal to the maximum of answer and profit of I n. Return the answer. That's it. So this is how you can solve this problem. The interesting thing is this simple thing. It looks such a small code. What I basically did over here is, in this I loop, I started a variable, local variable, and in the j loop, I'm including some jth item into that variable to take the maximum up to that jth item. And then I'm including in this. For this, what is needed? You just have to look at this, you just have to reach this formulation, and then you can generalize. You can say, okay, this is my formulation, and so these terms basically, I have to keep on taking them one by one. So first I take this one, then this one, then this one. I will have to take a maximum of them. And these two already have been considered by the previous state. So for this state, you just have to take this extra state. So dp of 2, 3, dp of 2, 3 will already have required these two steps. So I just need that extra state, this extra part for dp24. From dp23, this is the extra thing that I need. So I'm just storing them. It's not simply a dp state, it is dp state minus prices something. So that is the computation you need to do in the form of a local maximum in this case. The interesting thing is the code is small, everything is small, but this is such a useful technique, you find it so much in so many other problems. So let us see another problem. Maximum strength of k disjoint subarrays. Now this is slightly interesting. What this tells us is we have to select k disjoint subarrays. As I mentioned, this gives us a signal. We have n elements and we have to select disjoint subarrays, k disjoint subarrays. You can see this has been solved correctly by only 375 people, I believe, during the contest. So this tells you, okay, maybe during the contest only 319 accepted solutions. So this tells you something about the difficulty of this problem. Now, how is it being computed? Let's say you do it for x subarrays. So you select x subarrays and then you have to find the sum, the strength. Then you will say, okay, the first subarray multiplied by x, when it is x subarrays, first subarray multiplied by x minus second subarray multiplied by x minus 1 plus third subarray multiplied by x minus 2 minus fourth subarray multiplied by x minus 3 and so on. So if I take one example, let's say 1, 2, 3 minus 1, 2, 3. So the array is, or nums I think, the nums is 1, 2, 3 minus 1, 2, 1, 2, 3 minus 1 minus 2, and then k equals to 3, k equals to 3. That means 3 subarrays I can select. Now, first subarray sum will get multiplied by 3, then second subarray sum, am I right? First subarray sum by x, then minus second subarray sum multiplied by 2, again plus. This will happen alternately, minus, plus, minus. I mean, first it is plus, then minus, plus, minus, and so on. Plus to minus to plus and so on. So then plus is 3 into 3. Sorry, is 3 into 1. And what this means is, now I can segregate, I can say, okay, we can do something like I can select this in S1, this one in S2, and this one in S3. That is one way, in which way I will get 1 into 3 minus 2 into 2 plus 3 into 1, which gives me 3 minus 4 plus 3. What if I do in a different way? I say, okay, select these 3 in your S1, this one in your S2, this one in your S3. Remember, they must have at least one element. So I think that is given in the problem. So S1 into 3, S1 into 3 minus S2 into 2, once again same thing, plus S1 into, S3 into 1, which gives us 6 into 3, 18, minus 1 into 2, that is plus 2, plus minus 2 into 1. Okay, we can optimize it slightly differently, I think. Okay, sorry, I missed that last one. Last one is actually plus 2. So let me correct it. Yeah, over here it will be plus 2. I'm sorry. This is plus 2. So it is 18 plus 2 plus 2, that is 22. So you can see in the even subarrays S2, S4, S6, if I keep the negative parts, then that is good for me. My total thing is maximized. I have to maximize the final sum, the final strength, maximum possible strength. So if I keep the negative ones in the even ones and the positive ones in the odd ones, then that is the maximum I can get. And but still, that may not be always possible. For example, in the second example, you see 12 minus 2 minus 2 minus 2 minus 2. You can't take this one in the first one and then all the minuses in the second one. You can't do that. Third one has to be given something because you have to assign 5 different subarrays. So that is not always possible, that you only choose optimally, you give all the positive ones to the best ones and negative ones to the poor ones. You can't do that. So you have to respect this particular parameter, that is k. So how do you solve this? Over here, I can say, we can use the same technique. We can say that the sum, let's say dp of ij, if I have to define in the same way, how will I define? Here I should tell me how many, over there I was my number of transactions, here also I should be the number of subarrays, right? Because those subarrays I'm selecting successively, subsequently. So basically it is the maximum strength by selecting j disjoint subarrays up to index index j. Again, for convenience, I will assume that they are starting at index 1. So 1, 2, 3, 4, 5. Next, so there's the maximum strength I get by selecting j disjoint subarrays up to index j. Now, how can I form the states? I can say that, okay, if you again have to do, let's say, dp of something like the same thing, dp of 2, 4. For dp of 2, 4, this will be, again, it can be dp of 2, 3. And if you decide, okay, I will select up to the index 4, that means my last subarray will contain index 4, then comes the fun. Okay, from where to where? Let's say the last subarray can be only from 4 to 4. So up to the 3, up to index 3, you have the luxury to choose elements. So dp1, 3 plus the summation. So up to here you have got the dp, that okay, what is the maximum strength of selecting j disjoint subarrays? We can say selecting first j disjoint subarrays, the first j disjoint subarrays out of k, maximum strength. So let's say we have selected those first first I, right? First I disjoint subarrays, yeah. First I disjoint subarrays. So let's say we have selected the first I, first one, and then I will say, okay, then the second one, what should be the multiplier? The first one should have multiplier k, right? What are the multipliers? I can say first one, S1 will have multiplier k, and so I can say, okay, Si will have multiplier of something like this, k minus I plus 1. So this is the term that we will use, k minus I plus 1. So dp13, this is the maximum till that previous point, and then we will say, okay, the summation of j equals to, we can say, in this case it is simple, it is nums I only. It is nums of 3, right? Nums of 3. Nums of 3. Yes. Nums of 3 multiplied by that multiplier, which is k minus I plus 1, which is k minus 1 plus 1, which means k, multiplied by, here 2 is even, so in the even places we have negative sign, so we can say this will have a multiplier of minus 1. Next, my next state will have something like this. I mean, next possibility will be something like this. That okay, before that, up to the second element, it belongs to my previous transaction, belongs to my previous subarray. Up to there it can go, and this one will consider from nums2. So nums2 plus nums. Okay, I missed something. This will be nums4. This will be nums4 according to our one indexing. According to our one indexing, it will be nums4. So up to index 3, this is the maximum. Then after index 3, this is the only thing. Then I decide that okay, I will select these two elements. So I decided that okay, either it does not go up to the index j, that is this particular thing. It does not go up to index 4. If it goes up to index 4, then from where does it start? From where does the subarray start? So nums4 is always invert, but from where? So here I started at nums4 only. Here I started at nums3. These are my subarrays ending at the index 4. So this thing multiplied by k multiplied by -1. Next possibility is dp 1 plus nums of 2 plus nums of 3 plus nums of 4. Nums of 4 into k into -1. So these are the possibilities you have. You can have another possibility as well, which is dp of 1 0 plus nums of 1 plus all these things. Yeah, the entire thing you are saying that you will take in this particular step. Possible or not, etc. I'm leaving. You can judge that. Into k into -1. These are my possibilities. What is difficult over here? Let's say I have to now find, for this, I have, let's say, the values of these 4. Right? Now, if I have to go for 2, 5, what do I need? Eventually, I need the maximum. I need the maximum of these. I need the maximum. So basically, you can say somewhere I need the maximum of these things. And not just the maximum. Not just the maximum, I somewhere need, and not just this maximum. Actually, you can understand that I need the maximum of this entire thing. I need the maximum of this entire thing. When you move to dp5, then all these terms will change. This term will slightly change. Their indexes will just change. But these indexes will still be valid. One extra term will come. But over here, nums5 will get added to all of them. You can try in that way. Definitely you can try in that way as well. So you basically can say that okay, that is a common factor. So keep on adding that, but still when you move ahead, you know that is a common multiplier. You have to consider that in some of them at least. You have to consider that. So somewhere this will become slightly difficult to handle at some point of time, because at this 5th index, nums of 5 will come into the picture. Then at the 6th index, nums of 6 will come into the picture. And if you try to add nums of 5 to all of them, nums of 6 to all of them, it will become difficult. And if you say, okay, I will remember that for these 4, I will add nums 5. For these 5, I will add num6. That will become slightly difficult. So one way of looking at this is, instead of having so many elements, which is difficult to handle, 4 element sum, 3 element sum, 10 element sum, difficult to handle, we can look at this in a prefix sum kind of a way, right? This is a prefix sum kind of a thing. There's a prefix sum kind of a thing, so I can directly look at it in a prefix sum kind of a way, saying that okay, this is nothing but let me write it separately. Yeah. So when I say nums 3 plus nums 4, I can write that as the prefix sum of 4 minus prefix sum of 2. Nums 3 plus nums 4, that means 4th sum up to 4 minus sum up to 2. The next one I can say sum up to 4 minus sum up to 1. So prefix sum up to 4 minus prefix sum up to 1. Then the next one over there, you can also say the same thing. Nums 4, you can basically say the same thing. Prefix of 4 minus prefix of 3. And similarly, the last one will also be similar. Prefix of 4 minus prefix of 0. That means all the elements being added. Now, this is very similar to the formulation we did for our first problem. Why? Because this particular thing is common among all of them. So I just need to add this to each of them. I just need to add later on. And I think we did over there. Let us see. Yes, we were adding prices J. So this is that common thing. And what else? Yeah, prices J. Over here, basically this prefix of J I have to add, prefix of J. And, or rather prefix of J multiplied by minus K. That's exactly what I have to add. And then what happens? This DP 1, 3 minus pref of 3 into K into minus 1. DP 1, 2 minus pref of 2 into K into minus 1. It's trivial. So we can basically look at this in this way. That okay, now DP of Ij is straightforward. This is the maximum of DP of Ij minus 1 and the maximum of, and for maximum first take this into consideration. So it's prefix of J multiplied by K minus I plus 1 multiplied by minus 1 to the power K plus 1, you can say. From here you will subtract or you will add. So you'll basically add the maximum of I'm sorry DP of up to 3. So up to J minus 1. So max of L goes from 0 to J minus 1. DP of I minus 1 L minus prefix of L multiplied by the same factors K minus I plus 1 into minus 1 to the power K plus 1. So as you can see over here, now you can implement yourself the remaining solution, or you can wait to see for my implementation. What I'm doing over here is this is a factor which I need to multiply, and this is a factor common for the entire J. There is no change in this factor. This is independent of J. This is only dependent on I, K and I. So for any I can do this at a stretch. I can say, okay, from the beginning till the end, from the first J till the last J, I can keep on computing this in the same prefix some kind of a way. So for every J, for every L, I will do this. DP of I minus L minus pref of L into this one. The next L also I'll do the same thing. I will keep on taking the maximum. Okay, I'll go to the next L, I'll take the maximum, I'll apply that. Again, the next L, I'll take the maximum. On the next J, I will apply that, and so on. So basically, when I go to every J, what matters to me is up to the previous index, that is J minus 1. So the same way, when my J is equal to 1, I want only up to L 0 to 0. When J is 2, I want for L 0 to 1. When J equal to 3, I want L from 0 to 2. So if you have already the answer up to here, 0 to 1, from here to here you just need the second element, L equal to 2. So you just take this element and you take the maximum with that and you are done. You get this particular thing. So don't take this entire thing in your maximization function right over there. The variable that you're maximizing is going to be this part. This part you will keep on maximizing with every growing j. So that is the carry forward technique. So let us see my solution. I did exactly what I told you. If you focus on this particular place, previous to that I basically formed the base cases. If you focus on this particular case, I started with, since I'm maximizing, so I started with a minimum, which is something like minus of 2 to the power 55, where our answer can never reach. Whatever negative elements we have, our answers can never reach. So definitely our answer will be better than this. So I've taken this, and so that maximization will always bring our answer on top of this particular thing. That is how I've chosen this, but I've not chosen the long dot min value. Why? Because in case to this best before, let's say in best before you have this particular value, and then let's say that is the minimum long value. Now to that, if you add this particular thing, and let's say this thing is also coming out to be negative, let's say this is -1, so that means -1 into something, that also becomes minus, so minus something plus the longest minimum value, it will throw you into the positive side. That will be the bad thing. So don't do that. So basically be aware that you should not lead to overflow. That will become an integer overflow or long overflow, whatever, data type overflow. So that is the reason I took something below 2 to the power or minus 2 to the power 63. I took minus 2 to the power 55 over here. That is safe. You can take minus 2 to the power 60 as well. That should be fine. So you can experiment with that. So what did I do? I basically did the same thing. One difference from this calculation and my calculation, okay, there should be no difference. J-1, J-1, same index. So you can see, yes, same index. I'm using the same index, L. So yeah. So I'm saying whatever you have got till the previous index, just take the new one to that and then do this calculation. This is a safe thing that I did. You can follow this. That if j less than I, then this is not valid. If j less than I, that means I want I subarrays, but I'm not looking at I elements. I'm looking at less than I elements. Then no such selection is possible. In such a case, I'm saying that the answer is minus infinity. No such answer possible. So up to there, I'm basically having this so that no unnecessary plus minus happens. That is my strategy. So yeah. You can do this, and even in prefix sum I have here this is the base case, same thing for I equal to 1. Why I did this? Because I was doing I think I minus 2 somewhere over here, I minus 1, and over here okay, if I'm not doing I minus 2, probably you can push this thing also inside this one. But one thing is that over here I've calculated the prefix sum, and together with that these best values for the first thing, I found it easier to handle over there. But you can also pull this best thing. This is nothing but the DP state. You can pull this into this function. So that's it. Finally, you just return the last state. In the previous problem, we still have to take the maximum because at most k transactions. This is very clear. This tells k disjoint subarrays, not up to k disjoint. It says exactly k disjoint. So you don't have a choice. So you have to return the best of kn, not the best of or the maximum of best kn, best k minus 1n, best k minus 2n, and so on. You can't take the maximum. You have to take best kn, right? So those are the small things you have to tweak according to the problem. So yeah, my final problem will be from the Codeforces round 932 div 2. I had a separate video on this. Please watch that video on how I solved, how we basically solved these 5 problems. I think I discussed 4 problems B to E in that video, and I discussed, I think, 2 solutions over there. So in this problem C, you can see during the contest, I believe 1776 people had actually solved it, which is again, I mean, not very tough, but in that video I had actually explained how you can solve this using using the hash set kind of structures, tree set kind of structures. Even Tourist, the legendary computer programmer, the legendary grandmaster of Codeforces, had also used a similar set approach to solve it. you can see this C has lesser submissions, lesser correct submissions than D. So this tells you something about the difficulty of C. Definitely more people had attempted C and less of them have got it correct. Compared to D, more people attempted C, but less people than D got C correct. So this tells you something about it. Though I have discussed one approach over there, this is another approach, and this is mainly with respect to one comment that I got on YouTube. Um, One guy basically asked me to share this, that hey, there is another big O n square approach. So I basically shared the big O n square log n approach on that video, and that was also the complexity that tourists used. This approach definitely works, n square log n, but this can also be done using big O n square. And my dear friends, that is by using this prefix kind of technique. Using this dp plus prefix trick, you can solve that problem in the same way seamlessly, in a lesser time complexity, in a more efficient way basically. So let us see, and the code will also be far easier than what we saw over here. Here the code was still required a lot of things in to be carried out in mind. We have to do many plus minus over here, much carefulness over here, but you will see that that code, the code to that, the DP approach to it will be far simpler, and you have already seen the DP approach. So we'll just be using that over there. So let us see what is the problem. We have some messages, and then we have to select some messages P1 to PK. This is what we need to. This is the time spent for reading those messages, and then we have to maximize the number of messages we are reading. That is, we are reading K messages over here. For those K messages, this is the time spent. So we have to optimize the K messages, the time spent behind reading those K messages, and we don't have to optimize that. We have to maximize the number of messages by keeping this under a limit. So we cannot exceed L. This can only be up to L. The reading time can only be up to L. So this time has to be up to L, and we have to maximize this K. We can choose whichever K messages we want. They all have to be distinct. But then this one we have to obey. Reading time does not exceed L. So I would say that if you want, please go and see how we have solved it without this approach, because over here we are looking at one approach together. Go to that link and see how we have solved it. I pasted the link above. Go to that link, see how we have solved it using the using that particular approach of tree set. And then you can come and see how we do it using DP over here. There we have not used DP. We have really not used DP. But over here, DP makes it really simpler. So this is our expression. A of Pi, I goes from 1 to K, plus summation I equals to 1, K minus 1, B Pi minus B Pi plus 1. Now, whenever you have this sum of absolute value, okay, this is the time, and this time you basically have to keep as less than equal to L. So, and then you have to say what is the maximum K possible. So I can say, okay, I want the maximum K possible. This has to stay within a limit. So if I want to see that, okay, for any K, what is the minimum I can get, minimum time I can get? We don't have to minimize this, but still this has to stay within a limit. So one way can be, try to minimize this. Try to get minimum T for any K. So then what becomes the problem? The problem becomes that we can select K or K minus 1 or I, number of elements, number of messages. So K messages and we have to minimize the time. So here it is a minimization kind of a function. We have n messages in total, and we have to select K messages out of that. So out of n messages, we have to select K messages. So can you see the relation? If I basically say out of n messages, if I take K messages, what is the minimum time you can give me? And if I know this for every K, can I find out that answer from there? Can I say, okay, for every K, give me the minimum time? For whichever K, the time is the minimum. I mean, for whichever maximum k, that minimum time is basically less than equal to L. That k is my answer, correct? Right. So if I go there, if I go back there, you can say you can see n goes up to 2000, which means that n and k both are up to 2000. So n square algorithm will work for me. So my DP state can look like DP of I j, DP of ij, where I is, so basically this is the minimum time in reading, minimum time spent in reading I messages by only considering messages 1 to k, sorry, 1 to j. So I messages from 1 to j. If I take, then what is the minimum time spent in reading? Now, this particular term is fine. Take the minimum fine. But this particular term is a bit weird because this absolute value function needs a lot of minus plus adjustments, due to which we say whenever we have this, this kind of an absolute value function, if the elements are in sorted order, let's say ascending order, if the elements are in ascending order, then this can always be said as b of I plus 1 minus b of pi. So if sorted in ascending order, then basically it is the summation of a of pi plus, I can get rid of the absolute value. I can say, okay, I equal to 1 to k minus 1, b of, now no longer absolute value, b of pi plus 1 minus b of pi. What I used in my previous video basically was that this amounts to b of k minus b of 1. All the intermediates will cancel. B of k minus b of k minus 1 plus and so on. Basically it will start from b of 2 minus b of 1 plus b3 minus b2 plus b4 minus b3 and so on. All the intermediate values will cancel and this will stay. Bk minus b1 or something like that. Now, so this kind of an adjustment really helps. So we can sort it in ascending order. So that is the first thing. We can basically say, okay, we will fetch the pairs in some p, in some p. So we'll basically have, we'll sort by the b, we will sort by b, bi, and that will give us set of pairs p, where pi basically is going to have a and b. So PIs will be the pairs of A and B sorted in the order of B. We'll be using that. Now how to solve this? Minimum time spent in reading I messages by only considering messages I to J, 1 to J. Just think logically that, okay, if I have the answer for all lower states, how can I find the answer for DP? You can do it for, again, one example. So let's say DP 2, 4, same example I'm using. DP24. Again, I can say I will not consider jth message. So this closes all those possibilities. DP23. So 1 to j minus 1. By considering those messages, I've got the best. Next step is, if I, let's say I will consider the message 4. Then the question is, okay, if I consider message 4, this part is satisfied. This part I know, right? This part will be B of P of 4 or whatever. Correct? And so the previous element, what will be this I? That is the only question. So somewhere the question is, what will be this? Again, A of P4 also I'm considering. But the previous A's and this particular minus is what is new to me. So let us see what are the possibilities I have. If I say that, okay, the previous element to this was the third element. So this is the last element. Now I'll take this. Fourth element, I'll now take this. So I'll take, if I take the fourth element, that means automatically I'll get P4.A plus P4.B. What is this? Basically you can say A4 and B4, but when I've sorted according to the B's, at that time whatever is A4 and B4. So it is the pair for the fourth pairs A and B. This sum I'll be having the A plus B minus, if I say that before this fourth element the third element came, so I will say okay, then basically up to the third element whatever was the best you had, up to the third element whatever was the best you had, that is dp of 1 3, that is the best you had up to the third element, plus minus p of 3 dot b dot b. Yeah. There is one question over here, one big question. For this, one thing is necessary. I am subtracting p3 dot b, so definitely p3 dot b should be present. p3 dot b should be present over here, which means I may have to change this definition slightly, that hey, considering messages 1 to j and j must be present. So basically where the last message is the jth message, that has to be guaranteed. But what if that is not the case? Let's say I say that I don't impose that constraint. Then what can be the flaw? Then I can say okay, something with a lesser b. So some element which I am not considering. Let's say third element is not getting considered at all over here. Maybe second element was the last element over here. So I should have subtracted p3 dot b. P2 dot b. I should have subtracted p2 dot b, and I should have actually not subtracted p3 dot b. So you can say this is a non-existent answer. But actually the thing is, this will not impact the solution. Why? Because this will make the value lower. So it is the min time. P3 dot b will actually be, I mean, this might fall in the range. So this should be avoided, right? So I think this should be avoided. So forget this particular possibility. This is one difference from the previous problems. So forget this particular possibility. So mention this differently, that by where last message is message j, where last message is message j. So where last message is message j. Whether that will run or not, probably you can think a bit more, but definitely that was not a correct state. This is rather a correct state. So I will say that okay, if it is 4, that means the last element has to be 4. Please don't choose the last element as 3 or 2 or anything like that. So okay, the last element is 4, now we are good. Now I'll just keep on replicating these steps and say okay, what are my possibilities? The previous element can be 3, can be 2, can be 1, right? Two, 2, 1, 1. Yeah. And can it be 0? Well, for over here we are considering in one indexed manner, so not a scene over here. So yeah, these are the 3 possibilities. Now I can say now basically the recurrence becomes clear. How? What is my common? This is my common. P4 dot A plus P4 dot B. This is common. Right? This is common. What is uncommon? Those 2 parts, and there is a clear relation. dpil minus pl dot b. Clear relation. So I can easily formulate this, that dp of ij is equal to the max of. Now I can directly take this, that it is p4 dot a plus p4 dot b plus the minimum of L goes from 1 to j minus 1 dp I minus 1 up to L, exactly ending at L, what is the best, minus PL dot B, right? This is the final answer. This is the final answer. So let's take a look at my solution over here. Yeah. So you can see I have not taken dpij minus 1 over here. I have not taken dpij minus 1 because then it would have probably made it wrong. I rather just started with the maximum value because now I'm considering the min. So I started with the maximum value and then I said, okay, with that min basically keep on taking the min. So this is dp I minus 1 j minus 1 minus p j minus 2 dot b. Here there is an adjustment. So ideally they would have the same index, but this is an adjustment because my p's are basically indexed from 0 to n minus 1. So this is an adjustment, extra minus 1 factor here. And then dpij is equal to min plus this thing. So this min I have calculated in this way, math.min like this. So that is this particular min. This particular min is nothing but the min up to the previous L with this particular thing for this particular j minus 1, right? So yeah, for the j minus 1 I'm including that in this particular iteration, and the previous terms already exist. So yeah, over here I'm finding dpij equals to min plus the permanent values pi j minus 1 dot a, pj minus 1 dot b. And this is the final thing. I don't need the minimum time. What I need is what is the maximum value you can give me. So I'll say, okay, for every I am doing this. So the maximum I will come at the last. So I will say, okay, if the dp value is less than equal to L, take that I. For every j I'm doing this. If I do this only for the last j, that will be wrong. Because the j's I'm not basically recurring to the next stages. So there's one small difference from the previous problems. Again, a very good problem for this kind of a DP approach, and you can see this kind of overflow, this kind of a prefix kind of a structure basically helps us in solving it. This is my answer, and then basically, so this considers all the possibilities. If I say for I equals to 3, this will go through all the possibilities for I equal to 3 and give me whatever is the minimum time. That minimum time is what I need because I want to know that, okay, less than 10 seconds will it finish or not. So this will tell me, okay, with 3 people, 3 messages, you can finish in 8 seconds at the minimum. You need at least 8 seconds. So I say, okay, I'm fine with 8 seconds because I have 10 seconds quota. So I will take that. Then for I equal to 4, maybe, yes, for I equal to 4, that is for 4 messages being chosen. If it tells me, okay, you need at least 12 seconds, I'll say, no, I can't afford that because I have only 10 seconds as my quota, as my limit. So that's it. So I print whatever answer I've got at the maximum. So that's it. I hope you understood this particular topic. This particular topic will actually help you solve a lot of problems at a lot of ease in the coming contests. There are other problems also that I faced that I actually took a look at. Maybe you can try that yourself. I didn't get the chance to actually implement the problem. But there is this Codeforces round 933. Codeforces round 933 div 3. The problem E over here actually is quite good. So it has slightly more than that. It has this extra constraint that the adjacent supports must be no more than D. This imposes an extra constraint where you have to use a window kind of an approach, but you just have to add the window approach to the already prefix trick that we discussed over here. If you use that, and after that you have to do another small thing for this minimization, etc., another prefix kind of thing. But you can try it if you want basically one level above what we have basically done in today's session. You can try this problem. I think that way you can solve it. um, yeah. So that's it. I hope you enjoyed the session. There's a lot of effort that goes into these videos, so please do let me know how you felt about this, and please share with your friends who might find this video informative. Please do like and subscribe if you haven't done yet, and please do share, most importantly, with people who may find this informative. Till the next video, take care, keep coding, and see you all in the next video through the next contests. See you all. Bye.